All right. That's an overall of the service. Again, it's going to be coupled with the how-to, the step-by-step. I show you how to do it with a machine, without a machine, every step of the way, with the R134A machine, with the R1234YF machine, the dye, the leaks, all that is supplemented by videos. However, I felt it was important to go over it to make sure everyone's solid, because we're going to be rocking and rolling on components here. Now, compressor. It's known as the heart of the air conditioning system. Why? Because it does what the heart does. It circulates blood or refrigerant, in this case. The compressor itself creates the pressure used to change the refrigerant from a low pressure gas to a high pressure gas. Whoa, remember that. It's all about the change in state. But the change in state is induced by the pressure, because remember, pressure changes boiling point. So if we need to make the condensation occur 200 psi, that compressor needs to be able to make 200 psi. If we need 30 psi to make that evaporation occur in the evaporator, that compressor needs to be able to pull down to 30 psi. It has to. If the compressor can't keep up, you're not going to get the change of states. You're not going to have the correct pressures, and therefore you're not going to have cold AC. It's just not going to happen, right? And these compressors, they're kind of a wear item, right? So again, the compressor circulates, it pushes the refrigerant, moves the refrigerant through the tight restriction in the metering or the restriction device. Modern vehicles are belt driven, but hybrid vehicles and EV are electric driven. And we will cover that in the final unit. And they're really cool. Honestly, the electric driven compressors I think are nicer because you can run them slow, you can speed them up, you can run them while you're in the parking lot with the engine off the HV battery. You don't have to sit there and burn gas just to keep cool. I mean, they're nice, they're efficient, and they're actually pretty reliable, right? So there's a lot of different types though, right? We may have a swash plate, we may have a scroll, we may have a vane, we may have variable, and the variable could be different types. And so there's a lot of different types of compressors. And it's okay if you don't understand every aspect, but when you have a car that comes in and it's not blowing cold and you got some weird pressures and stuff, it's important that you understand what type of compressor it is, because some compressors will give you one symptom and some compressors will give you another one, right? But overall, if we got the high not high enough and the low not low enough, we're probably more focused on the compressor. Sometimes they make noise, sometimes the compressor clutch fails, right? Different types. So this is going to be a general lesson. It's generally on any type of piston compressor, but there's several types. So if the piston is going down, you can see it's trying to suck in refrigerant. This little reed valve needs to pop open this way. That's going to allow refrigerant in. Then when the piston goes up, it should slam this reed valve shut. See that? It slams the reed valve shut. And when it builds up, it's going to blow this reed valve open, right? So if you think about it, this is the suction valve and this is the discharge valve. When the piston comes down, it should pull refrigerant from the low side, fill the piston, the bore, the cylinder bore. And then when it pumps it, it should push it to the high side. Once in a while, what happens is it'll try to pull it from the low side, but this valve is broken. So when the piston goes down, it kind of sucks the high side down. And then when it tries to push it out, if this suction valve is broken, it'll actually push refrigerant back into the low side, and you'll get needles bouncing, and you might get the high not high enough and the low not low enough, and you're just going to get, sort of a mid performance out of it. Mid, I'm trying to use my vocabulary words. And, this valve could be defective. And to fix that valve, we need to replace the compressor. We don't really go in there. We don't replace reed valves. It's not what we do. We might send that compressor with a core charge back to the parts store, and someone may overhaul it, but the technicians, it's not really what we do. Makes sense? So this is assuming it's a fixed compressor. It has the same displacement. So every amount it pumps the full cylinder, the full stroke. Full stroke. When you want to turn it on and off, we clutch it on and we unclutch it off. So if you want that to run, there's no half. There's on, there's off. If it's on, it's pumping as much refrigerant as possibly can. If it's off, it's pumping nothing. Right. And that's old school. We've gotten more into the variable displacement compressor. So that can pump a little bit, 50%, 75%, 100%. It can move a different quantity of refrigerant depending on what it's calling for, right? When we'll get in there, it uses a solenoid and some things, but just know there's a fixed compressor and there's a variable displacement. Now, a lot of these, because it's variable displacement, we no longer need a compressor clutch. The compressor runs all the time. If we want no refrigerant flow, it'll just go to 0 duty cycle and it won't even pump the pistons. Then if we want 50%, it'll 50%, it'll move the pistons half. Then if we want 100, it'll do full stroke on the pistons, full stroke, right? But because we can go to 0, we don't really need a compressor clutch. We'll just have it run all the time. We'll just straighten out the swash plate and the pistons will do nothing and everybody's kind of happy, 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 right? So different types. Here's one of the old ones. This one is an old inline cylinder piston compressor. Pump, 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 pump. It looks like an air compressor, right? Huge, old, way outdated. We don't use those, but they were kind of easy to work on. You could pop the head off, you could replace pistons and rings and stuff. All right, here's an inline. This was a 2. So bump, 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 bump. Also old. Used to be used on used to be used on older cars with R12. Then we even got this V style. So this is like a V twin, like a Harley. Like this is an inline and this is a V. Right. Again, 60s, 70s, it was 40 pounds. I mean, it was big, it was easy to work on, but it's very inefficient. Now, back in the day in the 60s, we didn't care. Gas was cheap, cars were fairly inexpensive, emissions, like what emissions? There was no emissions controls. It was fine if this burned a lot of extra gas and made a lot of dirty air. Makes sense? It's just not where we were at. But in the newer ones, this would be a horrible idea. It's heavy, it's inefficient. Makes sense? So then we got a little newer Scotch yoke radial piston type. This was on a lot of GMs. It's round. It's kind of a unique looking piece of junk. This is also like it has pistons, right? So as this piece goes around, it's kind of wobbling and it's going to pull the piston in and push the piston out. Pull this piston in, push this piston out. It's got a suction and discharge valve. When it goes down, it pulls refrigerant in. When it goes up, the discharge valve pops open and it pushes it into the high side, right? So if you look at all these, there's something in common. There's pistons on pistons on pistons, right? And those pistons have little rings. And when the piston little Teflon rings get worn, they no longer make as much suction and they no longer move as much refrigerant. So you're going to have compressors that are not going to pull the low enough and they're not going to push the high enough. And the more miles and the more time, those little rings wear a little more and more. And next thing you know, your high is not as high as it should be. And your low is not as low as it should be, right? So in 3 different ones that we showed you, if your low is low and your high is low, don't be tripping on the compressor. That sounds like an undercharged. If your low is high and your high is high, don't be tripping about that. It sounds like it's overcharged. But if your low is not low enough and your high is not high enough, it sounds like your compressor is a little lazy, right? The compressor's job, pull the low, push the high. All these have pistons and stuff that wear out. Make sense? So that does happen. The swash plate in the middle, this is really hard to see, and I do have a couple animations, but this, we'll call this orange disc, is going to spin. And if it's a fixed, that swash plate's going to go like this, like that. So if a piston's on the top of it, it's going to stroke like this, boom, boom. The piston's going to poof, 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 right? So that's the swash plate. This one shows it pretty well, as you can see it spinning. The piston pumps over here, centers, pulls left, centers, pulls right, centers, left, right. So it's literally the swash plate is making the piston stroke right there. Okay, that's the swash plate. This piston has little bearings and stuff right here that's just going to ride across the swash plate. So how does it make it spin? Well, if you look at it, the belt is spinning this pulley. This pulley is connected to the clutch. And if the clutch is activated, it splines right into the shaft. And as this shaft spins, can you see how that swash plate is going to spin and move left and right? Right here. Centered left, centered right, centered left, centered right. It's gonna do this because it's a wobble. Generally we call it a swash plate. Cool. But remember, those pistons, they're in a bore. As this bore wears, as these rings wear, they're going to put out a little less and a little less. You ever notice sometimes you can hear the compressor, you hear a little boom, 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 boom. You can actually kind of hear the piston motion. Cool. Now, it'd be different though if one of these valves broke, right? If this valve was broke on the low side, you'd probably have a low needle like this. Yeah, it sucked it low and then it spit it back out. Sucked it low and spit it back out. Sucked it low and spit it back out, right? So some needle movements can tell you it's a compressor. Some needle readings can tell you it's most likely a compressor as well. Makes sense? So you should be able to visualize it. Cool. And a lot of times there's 5 pistons on this type, and there's going to be suction and discharge valves on both ends. So in a way, it's almost like a 10 cylinder, but it's tiny. Cool. And this one's a wobble plate, but these ones can be kind of similar to the swash, but you'll notice it's actually got like a little rod right here. It's actually got a little connecting rod. It pushes it back and forth. To me, I'll be honest, I think the swash plate's more efficient, but there are some wobble plates. It works really simple, but the piston doesn't ride right on the swash. It's actually connected with a rod to the swash plate, to the wobble plate. Cool. So it's kind of interesting. Again, what's it mean to you as a technician? Not that much. We're not going to rebuild these, but if you got a car that comes in with AC blows warm, you want to be able to visualize what's going on in that compressor. If the high is not high enough and the low is not low enough, you might want to think, well, maybe it's got piston ring wear and these types of, that's the type of stuff that we do. That's our job. Okay. Maybe not to rebuild it, but to accurately diagnose it. That is our job. Cool. And so we got a few different types here, and we could get in super detail. And when we tear some compressors down, I expect you guys are going to find different designs, different types, right? But so far, it's been a lot of piston types, a lot of piston type compressors. However, that's not there's your swash plate. But this one's different. Pistons are not the only type of compressor we have, but that's where we're starting. This one's unique, variable displacement. Interesting. So it can displace a little bit of refrigerant or a lot of bit of refrigerant. And it depends on the command of the computer. So we'll run duty cycle to a solenoid. That duty cycle to that solenoid will manipulate the refrigerant pressure, and it can actually change the angle of this plate. So if we were to run the plate really steep like this, that plate is going to throw really far. But what if we were to stand the plate up and have it just a little off? Then it would just go. That'd be a 10% displacement. This would be a 50. This would be 100. This would be a 0. Right? So the reason that this is nice, if you're in the parking lot and it's hot and you're at idle, this will throw 100%. Boom, boom, boom. It'll move a bunch of refrigerant. But then let's say you get on the freeway and it's, you're up to speed, and let's just say you're going up to Big Bear and it gets a little bit cooler. You may not want to turn the AC off yet, but you may be like, you know what? I just want to set it to like 68 and have it maintain it. Well, it's much easier for it to use this because it can actually start to do a little bit less displacement on there. If it does a little less displacement, don't you think that's going to save you some gas? It's more efficient for fuel consumption, MPG, more efficient for lowering your emissions. Cool. So these variable displacement are nice. Now, we could geek out on compressors if you want, but why this matters so much to you? Well, when it's a fixed displacement, you're doing your diagnosis from whether or not the clutch is engaged. When it's a variable displacement, probably there is no clutch, which means you got to do your diagnosis from the solenoid, and it can be a little bit hard to tell if it's commanded 0 stroke or if it's commanded 100 or whatever, right? So the way we diagnose these is just different. It's just a different diagnosis overall, right? So we need to understand how the system works. I gotta move this light coming in from that angle is kind of weird. There we go. We need to be able to know how to diagnose a fixed and know how to diagnose a variable. And you know, you'll get some practice with that, but I want you to understand what's going on. If it's variable, there's a solenoid that is going to change this angle of this swash plate, and we can command that solenoid to maximum stroke or minimum. But the thing is, if the solenoid's bad, we can't replace the solenoid. We can replace the compressor, you know, but you probably better make sure that it's gonna fix it, you know. So that's how they are. Now, getting away from piston types, we got scroll types. I'll show you one of these. This is like kind of oblong. It'll go around like this, and it'll basically like have an open port, suck refrigerant in, kind of squeeze it down, push it out, squeeze it down, push it out, squeeze it down, push it out. So you can see it pulls in here and it pushes out here. These wear as well. These also have a type of a ring, but it's not a piston ring. It's more of like a sealing ring that's in the shape of some of these scrolls. Kind of interesting type. Um, Same symptoms. It just might not make the same noises, but if this is weak, it'll start to make the high pressure not high enough and the low pressure not low enough. That's it. Not a real big deal. They also have these in fixed and variable. Um, Again, another bonus is they have a built-in oil separator, and they're used in certain hybrid vehicles. So this one kind of shows it. It's a little bit hard to show, but refrigerant will come in. This will kind of rock around, squeeze it, and force it into the middle. Force it into the middle. Boom, push it out, and then pull more in, right? So that's the motion. In, around, higher pressure, out the discharge at a high pressure, and then back to pulling refrigerant in, right? So that's how they work. This one's a little bit more simple. The rotary vane, positives and negatives of this, but the rotary vane spins. As it spins, these vanes will slide. Like this is fully compressed and this is starting to expand and compress, right? But they'll basically scoop the low side, squeeze it into the high side and shoot it out the discharge. Because remember, it's it's less, I guess, high and low. It's more suction and discharge. Blue is the suction, that's the low, and orange is the discharge, that's the high. Um, and you can see what that kind of looks like here, right? So as it moves, these vanes have to move. Sadly, though, because they do slide, sadly, though, those vanes will wear. And so in this type of compressor, this is one of the worst ones to fail because these vanes will wear and it'll send metal all through the system, which they can all do. But this one's a good design, easy to understand, but definitely like, you know, has the potential where if you have a compressor failure, this metal can end up getting put out the discharge and into everything, right? So if you have a compressor full on metal blow up, you got metal in the condenser, evaporator, the TXV or the orifice tube, you got it in the receiver dryer or the accumulator, you got it everywhere. It's a mess, right? And actually, we'd have to do a big flush, clean it all out, put the new compressor in. Sometimes they even will have you install an inline filter if it's got a bad enough failure and it's available. So right now we'll jump into the magnetic clutch that goes along with our compressors. The visual here is there's a bearing right here. If our clutch is not engaged, this part, this external part, the belt will spin it, but the internal part will be sitting still. Some of you guys got to see that on a couple of cars, like you got to see it on Mikey's last week, right? If the compressor clutch is not engaged, the belt is spinning, but this is riding on a bearing, and the shaft in the center is not turning. If the shaft in the center is not turning, look back here, it's not going to pump these pistons, right? If this shaft in the center doesn't turn, it doesn't move the swash plate, it doesn't pump the pistons. Make sense? So the thing to consider, there's two things to consider here. One, if this bearing out here was defective, when do you think it would make noise? This with the bearing that the clutch rides on. The answer is if it's the actual compressor clutch bearing, it'll make noise when the compressor is off. So when your AC is off, it's got to ride on that bearing. Then once you turn your AC on, this clutch, the silverish blue, will lock up with the yellow, and then it'll turn all as one, and that bearing no longer really does anything. So if it's noisy with the AC off, but it's quiet with the AC on, it's probably the compressor clutch bearing. But if it's the other way around, let's say with the AC off, it's quiet, but once you engage the clutch, it starts to make noise. It's probably inside the compressor, right? So back in the day, we used to replace just the compressor clutch, but now we're probably going to do both. There's been too many times where we pull it off, we put a compressor clutch on, it fixes the compressor clutch, but like the AC is not that cold because it's got 1,000,000 miles on the compressor. A lot of times we're just going to do a compressor. But you got to understand the difference for ASE, right? And then if you look at the diagram, this is your actual magnetic clutch. So your magnetic clutch is magnetic, and it's grounded to the compressor housing. So all it really needs is, it's not only that sun's chilling a little. So all it really needs is 12 volts right here at terminal 3. If it gets 12 volts at terminal 3, that is going to magnetize, and you're going to hear the click, and it's going to run, dum, 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 right? But what gives the 12 volts to terminal 3? Well, the relay, the switch side of the relay. 12 volts comes from IG1, goes through AC number 2, goes to both terminal 5 and 1, but it doesn't pass through to 3 until, well, 1 has 12 volts until, 2 needs to be grounded. And this is just a basic compressor clutch relay, right? You have to know this through and through because this will be on the ASE. So what's controlling it? Terminal 2 needs to be grounded. If we get 12 volts on 1 and 0 volts on 2, this will become the load and it will magnetize and pull the switch over, which will connect 5 and 3, which will give the 12 volts to the magnetic clutch and click, bum, 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 right? So what's really controlling it is terminal 2, which goes to connector 1, which goes to E38 terminal 20. Oh, the ACE ECU. In this case, the ACE ECU controls that. So when you push the little green button, you're basically giving ground to the relay in this example. Cool. Now, in some other ones, it's going to a lot of times be the ECM. The ECM actually controls the magnetic clutch relay. Now, when we get into automatic temperature control, you got to understand we've got air conditioning control panel, which has its own logic and it's controlling the servo motors, temperature doors, etc. But it's also the AC switch that you press gives a signal to ECM, but ultimately the ECM's got to reference some things like the pressure switch so it doesn't run it without refrigerant and blow it up, like the evaporator temperature sensor. In case it's freezing the evaporator, the ECM will kill the magnetic clutch relay, so the evaporator won't be so low. It'll start to come up a little higher, and higher pressure means higher temperature, and it'll defrost or thaw it out, right? So once you get into this is more current. This is where we're going to make our money. You got to be able to understand its inputs, its process, its outputs, right? The computer is controlling the AC clutch, but the computer is looking at inputs to determine if it should turn that on or not. Okay, Rotseni, go ahead.
So the signal from terminal 2 to E38 is that 12 volts or a signal voltage?
All right, let's break it down. We got 12 volts right here because it's on a fuse, right? We don't fuse grounds. So if it has 12 volts on terminal 1, what would we need on terminal 2 to magnetize that, to make that active? Picture a light bulb. How do we turn the light bulb on? If you got
So
12 volts on both sides, that light bulb ain't gonna work, right?
Needs to be grounded.
Exactly. So the AC ECU is providing a ground to terminal 20, and that combined with the 12 volts will make this active. And that'll magnetize this relay and pull a little switch over, connecting 5 to 3 and sending voltage to the compressor. Right? Everybody cool? Anything like that? Stop and let's sort it out. Everybody needs to be crystal clear. All right, and this one was basic. This is old school, and this one's really not that different. When we say the magnetic clutch relay, it's pointing at this and it's saying to control the relay, which controls the clutch. That's really the same as this. It's just this is showing you it's a little more multiplexed. The AC control panel gets an input from your AC switch. It also controls your blower motor and stuff like that, but then it also provides an output to the ECM. Now, this might literally just be a 12 volt or a ground signal, but if it's truly multiplexed, they'll both be on the CAN network. And the AC control panel will communicate to the ECM, and the ECM will execute, commands, right? So without making it too crazy diaget, you just got to understand this is all stuff that's happening. So like if we have the low pressure switch, the AC pressure switch, that's going to the ECM because if we have low refrigerant, the ECM will not turn on the magnetic clutch relay. So like you could jump out of the relay and tell a lot about what's going on, but ultimately you may have to determine, does it have enough pressure in it to even allow the ECM to try to power that relay? Or in this last case, technically to ground the relay, which will provide the 12 volts to the compressor clutch, right? So overall, it's pretty good. Here's that variable compressor again, and this is just showing the duty cycle. The computer, like right here, is controlling the magnetic clutch relay, but if we had that variable displacement, it wouldn't be controlling the clutch relay. It would actually be comparing the solenoid. It could do 100% stroke. It could do 0% stroke, right? See the difference there? This is going to stroke full. This is going to stroke zero. The computer will control that. The computer will control increase the stroke or decrease the stroke. If the cooling load is up, the computer will say, hey, solenoid valve, max out, swash plate angle greater. How does it determine the cooling load is up? Well, a lot of times it'll look at various temperature sensors, right? The cooling performance will go up because, right? But then let's say the cooling load is down because you're heading up to Big Bear, which would be a great idea. Have you seen the temperatures there? At night, it's like 50, like not 59, like 50, like 49, like nice. All right. But if you head up to Big Bear and all of a sudden you get there and it's like 68 degrees and kind of cloudy, their cooling load went down, right? It's going to send a signal to the solenoid control valve, open, discharge pressure down, crank pressure up, swash plate angle less. That's going to put the cooling performance down. It's not going to cool as much, but you know what's cool? You don't need it to cool as much. Hilarious. Better for gas mileage, better for emissions. Cool. So again, that's the solenoid control type. Make sense? Magnetic clutch. This one has a damper pulley, dampening limiter pulley. This is on all the time, but that's okay because it's got the solenoid that controls the swash plate, right? So if you want this compressor off, stop sending 12 volts to the compressor clutch. If you want this compressor off, this is on all the time. So you'd run 0% duty cycle and that'll level your swash plate and the pistons will no longer pump. Easy to diagnose, harder to diagnose. The variable displacement's a little harder to diagnose. You can't simply see if it's on or off. Make sense? You just can't. Cool. So the new stuff, variable capacity, a lot of times these have breakaways. So if your compressor locks up, it's designed to break away so that your belt won't fly off and leave you stranded, right? So that's, and they also absorb fluctuations. The pulses, dampening, it does a lot of stuff kind of like kind of similar to a harmonic balancer with a breakaway. Cool. Then the other thing is, and this one's a little Toyota specific, sometimes they have a lock sensor. So there are some compressors where they put a sensor in there and a speed sensor with a reluctor. And if the compressor shows locked up, it'll stop sending voltage. It'll shut the relay off. It'll shut the relay off because we don't want to try to lock a compressor when the compressor is seized because that'll blow the belt off. So this is not usually an ASE one, but just so you know, that speed sensor, if your engine is turning and your compressor speed sensor is not, and the compressor clutch is on, it knows the compressor's got to be locked up, right? And that'll send a signal to the ECU, compare the rotation speeds, and if it's locked up, it'll disengage the compressor clutch. A little overcomplicated, but do you know why Toyota did it? So you don't blow the belt off when the compressor locks up. That's the whole, it's just for your convenience as the driver. Cool. And then additionally, we can have some errors in the system. So if we get pressure that's too high, let's say it was a turbocharger. If your pressure was too high, what would you do to vent it? Sort of trick question. I mean, normally we do wastegate, right? And that's going to decrease the speed of the impeller and turbine. But if you actually already had too much pressure, we'd actually have a blow-off valve. Like all these noises, right? Those noises you hear generally are actually the blow-off valve, especially when you let off the gas real quick. Your compressor's still really spun up. All of a sudden, your engine, throttle closes. It'll build up a lot of pressure in the charge tubing and these sounds. Well, AC compressors got one too. That's a oil compressor pressure relief valve. So if your high side pressure gets too high, it'll actually compress a spring, unseat, and go. You know the problem though? It shoots refrigerant and and oil and possibly dye all over the compressor. Then you're thinking the compressor's leaking, right? And then come to find out somebody overcharged it. It blew oil and dye everywhere a few times until it was no longer overcharged and now it's fine, right? So you all need to know on the compressor for protection of the compressor, it does have a type of a blow-off valve, a PRD, if you will, pressure relief device, pressure relief valve. Cool. So, a lot of times it's 500 PSI though. We really should not be seeing 500 PSI. And if we do, something wrong. Am I right? This is purely mechanical. It's just a spring and seat. This is a cycling switch, and there's a lot of different types of switches. Switches are old school. This was just on or off. So like if this is on an accumulator and it's a cycling clutch orifice tube, in other words, um, orifice tube style, it'll turn the compressor on. And then if it gets too low, this will actually open and that'll interrupt the voltage going to the clutch and it'll disengage the clutch, right? So this is like a low side cycling switch, right? When the low side is not low enough, the compressor runs to try to suck the low side down. But once the low side gets too low, boop, it opens up and it kills the compressor clutch. And when you shut the compressor off, the low side was really low, it starts to come back up. And once it gets up high enough, click, it closes those contacts, which sends the voltage to the compressor clutch. Click, it's back on. And as it's back on, the low side pressure is getting low, low, low until it gets too low and it opens the contacts, which interrupts the power again. Makes sense? So that's why it's called a cycling switch. And the low side cycling switch, that's what it does. And if a low side cycling switch was no good, it would never make contact. It would never send voltage to the compressor clutch. It would never run the compressor. So you might have an AC blows warm, full of refrigerant, healthy compressor, but you might have a bad cycling switch. How would you test it? You can test continuity, you can test voltage drop or available voltage. Cool, because it's that's how we do it. All right. Or we can also have multiple different switches. So like we could have a low or a high cutoff switch. Let's go with this high cutoff switch. If your high pressure gets, let's say, above 400, this high pressure cutoff switch will close and it'll interrupt the compressor clutch, or it'll open and it'll interrupt power to the compressor. So the compressor will shut down and that'll come down. Typically, we don't have a high pressure cutoff switch and a relief valve. A lot of times we'll have no compressor cutoff switch and just a relief valve. But if it has this, it should stop at 4 before it ever reaches 5. So you may or may not see a compressor relief valve, and you may or may not see a high pressure cutoff switch. It may have one or the other, but probably not both. And sometimes neither, because this is a trinary switch. It's combined high-low side cutoff switch. A lot of times they'll put it in a location, or they can be kind of funny. Sometimes they even do temperature cutoff switches, and then other times like switches can only do so much. It's either above a number or below a number, right? But what I really like is a sensor. So this is a pressure transducer. Transducer is another name for a sensor that takes pressure and makes it into voltage. I like the pressure transducer, the pressure sensor, because if you wanted to roll out to the car and check the pressure, you could do it with the tech stream. Now, a lot of times they'll only have one, but if you went up to it and you turned the key on but didn't start the car, you could check the static pressure with the scan tool. This will tell you the static pressure. Now, once you start it, if it's on the high side, you can check the high side. But if it's on the low side, you can check the low side. A lot of times on the high side. Right? Now, I like that because that is a more clear picture of what the pressure is, what's going on. The cutoff switches are okay, but the pressure sensors, very, very chingon, like that. You know what I mean? Very, very chingon. How you test these are way different. Back to here, it's continuity. If the switch has got contact, it's got good continuity, low resistance. If the switch has got bad contact, it has bad continuity, high resistance. You can check it with resistance, you can check it with voltage. If you have 12 volts in and 0 volts going out, the switch is open. If you have 12 volts going in and 12 volts going out, the switch is closed. Cool, chilling. With this, we would have to check a 5-volt reference or maybe a 12-volt reference. We'd have to check a ground. We'd have to check the signal voltage, which will vary between about a 0.5 volt and a 4.5 volts. 0.5 volt generally being low pressure, 4.5 volts generally being a very high pressure, right? So a little harder to diagnose, but not a real big deal. We'll get into covering each of these. Cool. And then if it's a temperature sensor, that's a thermistor. So sometimes we'll put temperature sensors for ambient air because that's a relevant information for our variable displacement compressors. Sometimes we'll put temperature sensors on the evaporator. We don't really put them on the condenser, but on the evaporator, if the evaporator gets too cold, it'll freeze up. It's kind of hard to have air blowing through your HVAC box when all the moisture hits the evaporator and freezes and turns that thing into a big block of ice. Right? So sometimes we will have a evaporator temperature sensor in there. And it's just a thermistor. And a thermistor is the backwards of nature, right? So almost all materials, as they get hotter, the resistance goes up. But a thermistor, see, they're backwards. As the temperature gets hotter, the thermistor resistance decreases. And that's what makes them really reliable for temperature sensors. And we'll go over how to diagnose each type of sensors. This class does have some electrical in it. How to diagnose switches, relays, clutches, temperature sensors, pressure sensors. Like we're gonna look at some diagrams later. Right? That's the main thing. And they also do have pressure switches. Sometimes they're wired up together. Like for example, the low pressure switch is normally closed. The high pressure switch is normally closed. If your low pressure gets too low, it'll open which will cut power to the compressor. If your high pressure switch gets too high, for protection, it'll open, which will cut power to the compressor clutch. See how we can use a lot of them in series? We'll just put them in series. Boom, boom, boom. Cool. They're interesting way of doing it. Right. And there are different ways. Okay, and you can see what happens. Cool. Now, if we were to look at a pressure switch on the EWD, a lot of times it'll show normally open, normally closed, right? You can get the terminal numbers. You can do a lot of your diagnosis right there. It's not hard diagnosis. It's just switch diagnosis. It's pretty simple. Cool. And the pressure sensor, like I was saying, if you have 0.1 volts, that would be out of spec. If you have a 0.1 volt reading on there, you're going to get a code. The circuit's open or shorted to ground, right? But if you have a 0.5 volts, that's about zero. If you have a 1 volt, that's about a 57 psi. If you have a 4.8 volts, that's about 463. That's pretty high. If you have a 4.9 volts, that's off the charts. That means it's either got an open ground or the signal is shorted to the 5-volt reference. Make sense? So they give you this range. That should be between a half a volt. And actually, this one goes up a little higher than 4.5. It goes all the way to 4.8. Half a volt to 4.8 is legit. Those are real numbers. However, if it's below a half, there's a problem in the circuit. And if it's above a 4.8, there's a problem in the circuit. Makes sense? If it's below a half or above a 4.8, it's going to set a code. It's going to have a DTC. At that point, we're really just doing DTC diagnosis, EWD stuff, like make sure it's got the 12 volts, make sure it's got the ground. You can check the signal wire, right? Some stuff that we'll get really in detail when we do diag, but this is an overview of all the components. So I gotta at least tell you about the components. So when we do the diag, you're like, oh yeah, I remember the pressure sensor. I didn't totally understand it, but I know that it's screwed into the line and that it's going to give me a different pressure it's going to give me a different voltage depending on the internal pressure. But that pressure would never exceed those normal numbers. And so therefore, if the voltage is below a half or above a 4.8, there's a problem in the circuit. Make sense? The circuit technically could be the sensor itself, but it's an electrical problem, not a pressure problem. Cool. And then sometimes the compressors even have a mass sensor where they'll measure the mass of refrigerant flowing. So they'll actually tell you how much is flowing. Cool. And so you guys, I think that's enough. I'm on slide 108 of 204. So this thing's a beast. And I want to let this settle. The next thing we'll be into is lines, connections, evaporator, condenser, TXV, orifice tube, right? So the main bulk of it was the overall AC service and everything to do with compressors and how the compressors are commanded with sensors and switches, okay? So not a whole lot of electrical in the second part, but how you guys feel? You hurting? A little bit?